Alright guys, we're going to start with gas laws homework number 6, and because it's at the beginning, I'm going to start with number 1. A sample of carbon dioxide with a mass of 0.5 grams is placed in a 400 milliliter container at 350 Kelvin. What is the pressure exerted by the gas? Let's write down what we know to start off. We're using a sample of carbon dioxide, that's a good thing to know to start, with a mass of 0.500 grams. Okay, we're in a 400 milliliter container, that's going to be our volume. At 350 K, that's going to be our temperature. And I think that's all we know. We're looking for the pressure. Sweet. We're going to need the equation PV equals nRT over here, which is awesome. We have a P, or at least we're looking for a P. We have a V. We don't really have an M yet. We know what R is, and we have a T. The way that we're going to find that N, that number of moles, is to use our mass. So we're going to use this number right here to find our number of moles. I'm going to do this in purple just so we can keep it straight. We've got 0.500 grams of carbon dioxide gas. And this is, yeah, I know this looks scary, going to be a T-chart. This is going to be a stoichiometry problem. If we look at carbon dioxide, we can find the number of moles by using the molar mass. Carbon is 12.01, oxygen is 16. 16 times 2 is 32, plus 12 is 44. So we're going to have 44.01 grams of carbon dioxide and 1 mole of carbon dioxide. Our units there are going to cancel. When we take that, excuse me, that 500 divided by 44.01, we're going to get 0.0114 moles of carbon dioxide. That is going to be our N. With that information, we can really get going here. There's one other thing that we need to do before we get started, and I'm going to just point that to you down here. 400 milliliters. Milliliters is not how we roll. For our volume, we need 0.400 liters. If you're looking for the conversion factor for that, then just divide that by 1,000. Okay, I'm going to move us down here, and I think this is where we want to be. And I'm going to do this in red. We've got PV equals nRT. We're going to solve that now for P. The way to do that, I think you all know this, is just to divide by V. So that's going to give us P equals nRT over V. At this point now, it's just a plug and chug sort of a problem. Very, very simple, very easy. And we'll plug and chug right here. We're going to have P equals that 0.0114 moles times R, which as you recall is I need to find my undo button here. Here's my eraser. There we go. Sorry, I'm still getting used to this thing. 0.08206 liters ATM over mole K. I'm running out of room here. And then our temperature, forgive me, 350 Kelvin. I know that you know what that means. And then our V on the bottom is 0.400 liters. I'm going to move us down just a little bit further here. When we plug all that in and we get our P out, we're just going to take that 0.114 times 0.08206 times 350. Our answer there is going to be P equals 0.82 atmospheres. And that is with sig figs. In our problem there, we have a 350 Kelvin. I'll move that back for us just a little bit. Right here, we have the 350 Kelvin, so our answer should be 0.82 atmospheres. I'll erase that one, and let's go ahead and move on to number 3. Now this is another PV equals nRT type problem. What pressure is exerted by N equals 0.450 moles of gas at 25 degrees Celsius, so we know that our T is 25 degrees Celsius. If it is contained in a 0.650 liter vessel, so 0.650 liters is our volume. And again, we're looking for pressure. The only conversion we have to do here is that 25 degrees Celsius. 25 plus 273 is going to be 298 Kelvin. With that, I think from the last problem we'll remember that P equals nRT over V. If you disagree with that or don't remember how to find it, go ahead and rewind this video a little bit. But we just did that, so I think you're probably all comfortable with that. And now we can just plug stuff in. So I'll switch up the color one more time just to keep you guys guessing a little bit here. We're going to have P equals 0.450 moles. R is that 0.08206 liters, atmospheres per mole Kelvin. Our temperature is 298 Kelvin. And all that is going to be over 0.650 liters. I apologize for my messy handwriting. I think you get the picture. When we plug all that in and divide by the 0.650 liters, our pressure here should be 16.9 atmospheres. Now, you're probably freaking out saying, hey, that can't be right. In our problem, we had 2 sig figs, right? Yes, that's true. However, in our answer we need to have 3 because when we add, we're going to add 273 right here to get our 298 Kelvin, which is awesome. This number, all 3 of those numbers are significant because we added. So that 8 is significant. So truly, our answer should have 3 significant figs. It should be 16.9 atmospheres. If you've got questions on that, ask me in class. I know that sig fig stuff gets a little crazy. I'll go ahead and pull this up so you can see it just one more time, and I'll erase it and move on to number 5. On number 5, it says how many moles of gas are in a balloon that has a volume of 15.9 liters at a pressure of 149 kilopascals and a temperature of 28 degrees Celsius. We'll get our information up on the board here. Our volume is 15.9 liters. That's awesome, and the units are correct and everything. Our pressure is 149 kilopascals. Our temperature is 28 degrees Celsius. When we add 273 to that, we're going to get 301 Kelvin. All 3 of those numbers are significant. And we're looking for the number of moles. Our units here are really nice except for the pressure, and we're actually going to have to do a unit conversion here. And if you look at your unit conversion sheet, your unit conversion from kilopascals to atmospheres is 101.3 kilopascals per atmosphere. When we take that 149 divided by 101.3, what we're going to get there is 1.471 atmospheres. And I know I've got an extra sig fig there, but I'm going to leave that just because it looks cool. No, just because it'll help us to be more accurate in our calculations, honestly. So we're now ready to plug stuff in, and we'll go ahead and do that here. Whoops, sorry about that. I'm going to erase that really quick. Again, we want the PV equals nRT, and we're going to solve it now for n. So that's going to give us PV over RT equals n. And we can start plugging some stuff in here. N is going to be equal to that 1.471 atmospheres times our volume, which is 15.9 liters, over the 0.08206 liters ATM over mole Kelvin. and times, that is not a 3, sorry about that, 301 Kelvin. I'm going to move us just a little bit here. When we run through all that math, our N, or our number of moles, equals 0.947 moles of whatever gas we have. Again, this should be 3 significant figures. We've got 3 here, we've got 3 here, and we've got 3 here. So we're good with the 0.947 moles there. Hope that went all right. Hopefully that answers any questions that you might have. If you have any others, please let me know. Have a good evening.